Okay, CR5. So in this problem, um, let's see. So the first part of this problem is to figure out what really depends on what. And we say here partial of q with respect to y. Well, what does that even mean? I mean, what's a function of what? We really need to kind of diagram these variables. So there's 7 different variables running around here. It's kind of annoying, and we just kind of need to get everything organized. So note from the very beginning, p is a function of u and v. So what I'm going to do is I'm going to write that down. I'm going to sort of start forming a little diagram here. And p depends on u and v. Now v is a function of x and y. So that v is a function of x and y. Let's do that. Now w is a function of x and y. Okay, well x and y are here, so we need w there. Next equation, q is a function of v and w. Q depends on v and w. And u is a function of x and y. Well, good, I already had that kind of in position. U is a function of x and y. So this is sort of the diagram of. Now I'm not going to draw all the lines here because there's too many, and the point is that all of these depend on all of these, and all of these depend on all of these. So I'm just going to write it like this. Yeah.
Is there a formal name for this diagram?
Not really. It's just kind of the flow of dependencies, I guess. I don't know that it has a name.
You write it from right to left.
Yeah, left to right. I think you meant. Yeah. So yeah, going that way. Yeah, that's typical.
Okay.
Yeah. So with this now, when the problem says partial of q with respect to y, okay, we're trying to take the partial of that with respect to that, and now we can see, okay, well, there's 3 independent variables. 3 intermediate variables in there, and so the way I'm going to write down partial of q with respect to y is by using these 3 intermediate variables. So I'm going to say it's partial of q with respect to u, partial u with respect to y, plus partial q with respect to v, partial v with respect to y, plus partial q with respect to w, partial w with respect to y. And I claim that each one of these partial derivatives is something that you can compute. So for example, what's the partial of q with respect to u? Well, here's how q depends on u, v, and w. Note that there are no u's in there. So the partial of q with respect to u, this here, is 0. So I don't even need to really bother with the partial of u with respect to y. There's just no point. Okay, so next thing, what is the partial of q with respect to v? Well, looking at that highlighted equation, the partial of q with respect to v is clearly 1. Right? Now, next thing, what is the partial of v with respect to y? There you go. Partial of v with respect to y is, well, again, you look at that equation, -1. You know? Does that make sense to everybody? You okay?
Yeah, but I don't really know how can we draw this diagram.
Well, so because the way the functions are given here, so you see that p is given as a function of u and v, and so that allows you to say that p has to be 1 step over from where u and v are. Now there might be another variable w. It ends up there's another variable w that sort of has to be in here also, but p had to be 1 step over from u and v. And then you sort of piece it all together. I mean, so every little step. So v is a function of x and y. Okay, well, that has to be 1 step over from where the x and the y are. I mean, the variables have to fit together in some way or another, and you see from the equations that you're given that you can assemble this sort of collection of dependencies.
If we want to find the partial partial derivative
Yeah.
of p.
Of p?
With respect to y.
Okay, sure. Well then, okay, so we're in this problem here, we were doing q with respect to y, but if we ignore this and suppose we want to find the partial of p with respect to y, then there's, again, 3 intermediate variables. And we'd take the partial of p with respect to u times the partial of u with respect to y, plus partial of p with respect to v times the partial of v with respect to y, etc. I mean, again, you have 3 intermediate variables, and you write down something kind of like this, just with p instead of q.
But actually, we don't know the relationship between p and w.
Well, here's a formula for p. I know exactly what the relationship is between p and w. P does not depend on w. That's what the relationship is. P is exactly this. P is u minus v. Done. There's no more to know about p. That's exactly that. This is what this sign here means. This is exactly what p is.
So that is 0.
So yeah, that's right. So that's why, yeah, exactly. If you're taking the partial of p with respect to w at some point, 0. Yep. Yeah, sure. So let's just wrap up this problem. So we're looking at the partial of q with respect to y. So that was 0. This therefore doesn't matter. These we could compute directly. What's the partial of q with respect to w? Let's see, where is q? Here's the formula for q. Partial of q with respect to w is negative 2w. And now partial of w with respect to y, well, that's 1. So altogether, what you have is it's negative 1 minus 2w. There you go. Now, by the way, if you want to sanity check this, and this is not a terrible idea, by the way, don't do the following on an exam because this bypasses the clear intent of the problem. But one thing you could do on a just for a practice side sheet of paper, just for what I like to call a sanity check, is let's write down exactly what is q. Well, q is v minus w squared, and let's see here, v is x minus y. Now let's say minus w squared. What is w? Well, w, there it is, 3x plus y. And you could just multiply this out, right? And you get x minus y minus 9x squared, let's see, minus 6xy minus y squared. That's q. I've found this function, q is a function of x and y explicitly. And now I can just take a partial derivative of this with respect to y. And I get, well, let's see here, negative 1. Let's see here, minus 6x minus 2y. And by the way, note that this, if I were to rewrite this, negative 1 minus 2, let's see, what was w? W was 3x plus y. That becomes negative 1 minus 6x minus 2y. And those are the same. So this is just a sanity check. Now, again, on an exam, and by the way, I've written about this on the class webpage just for reference. But on an exam, when the clear intent of the problem is to use the chain rule, if you do this, I'm going to consider you're sort of obviously circumventing the intent of the problem. You're not giving me what I clearly wanted to see. So the fact that you get the correct answer here does not get you full credit, right? So part of the problem is to make sure to understand what the intent of the problem is, and to give me what I need. So don't do this on an exam, but just as a sanity check to make sure that this is actually computing the right thing, we can see that, yeah, sure enough, it does. Yeah. Does that make sense? Okay.
But actually, I have another kind of
Another kind of what?
And then we can draw it in another way.
Oh, okay. Hang on a sec. Let me stop this recording and then, or did it? Yeah, go ahead.
Do we have to specify DQD at mu or u?
Right here?
Yeah, when we know Q does not depend on.
Well, you have to write this down just to have a complete, chain rule discussion of this partial derivative. You've got to write down all three terms. Now, you're right. This does end up being zero.
Right. If you look at the equation, Q equals V minus W squared.
Yeah. I'm just saying if you didn't write this down at all, then it kind of looks like you ignored the U variable. But note, all you got to do is write that down, observe that that's zero, and you're done, right? I mean, how hard is it to write that? It's not that bad to write. It's just not that much. And now I know for sure that, having written that down, I know that you realize that, well, here's all the intermediate variable terms, and so I know that you did it in a reasonable way, right? So I think it's a little bit more complete to write it down, even though you're right. Of course, it doesn't actually make any contribution to the final answer. Yeah. Okay, let me stop this recording, and then I'll look at what you've got there.